Hello, everybody. Um, I do not really know from which time zone you're um, seeing me from, but then yes, I'm assuming that you're having a really good day, and in case you're not, I hope you would have a good day, and a really cool week ahead. So, just a quick introduction about me. My name is Jasveen, and I'm basically from the southern state of India. So, India, which is basically in Southeast Asia, or I would say South Asia. There's this another state in the southern part of India, and I'm right in the middle of the southern state. The state is called Telangana, and I'm from Hyderabad. So, greetings from Hyderabad. So, I'll be talking about my speech or my session is about how drastically will NLP as a computer software change our lives in the near future. So, what we're seeing these days is NLP as a computer software is progressing great. I mean, just a couple of days back, we had the GPT-3 model by OpenAI, and we already had the existing previous models by OpenAI, and we have a lot of open source work going on. But what we eventually are not seeing, or I would say what we're ignoring, is that NLP has a great potential, but it's not being unlocked at the same pace. Probably blockchain or AI or any of those like terms are being done. So this is a small introduction, or I would say a small talk on how I feel NLP can be used for the near future and what sort of work I have done in relation with this talk or in relation with this session. And I hope there would be good takeaways for the home. So on that note, let's start. So I am basically an undergraduate researcher at a lab called Anusaaraka, which is the largest speech and language translation lab in South Asia. The lab's name is LTRC, and I'll work in one of the labs called Anusaaraka. So Anusaaraka is basically computer software, which I would say it works at rendering text from one Indian language to another. But the catch here is you do not specifically have to think of it as a machine translation system, because this is something much more beyond the lens of machine translator system. Because when we have a machine translator system, you just input a probably sentence, like let's assume you want to translate it from English to German or English to French. You just you just put in your English word and you say, just convert it to French, and Google Translator, Bing, it brings you the result. But there's no sort of transparency. There's no sort of I would say, the flow of instructions. It does not really tell us how it caught that, but it just caught that. And I feel that it does sort of an injustice to the future we're looking forward to NLP, considering what GPT-3 has already done. Let me explain it more briefly. So Anusaraka is basically computer software, and what we do is it produces an output which is obviously comprehensible to the reader, but it might not be grammatical. So what that means is, let's assume I have a machine translation system in Anusaraka running from one Indian language to another Indian language, and my output is supposed to be in Hindi. So my output in Hindi can be understood by a Hindi reader, but it may not be fully grammatical. So what that means is the reader will require some sort of background training, so that he require a sufficient amount of training so that he can understand the output, because it grammatically might not make sense, but its efficiency in terms of the translations would be very, very good and pretty high. So this is a sort of overview of Anusaraka that I have to give, because the work of NLP, the research work that I've done, is closely related to Anusaraka. So that is what I thought it would make more sense bringing this in. Next, so you have heard a lot of people talking about NLP. You have read a lot of tutorials online. There's Coursera courses coming up, but one of your most basic doubt is, what is NLP, or what is natural language processing? There's a lot of hype, and I would say that NLP at the end of the day condenses down to these six things. The number one is text processing. Second one is syntactical parsing. Third is entity parsing. I'll be talking deeply about them. So just giving you a brief of, once entity parsing happens, there's statistical features which involve a lot of stats, probability, and maths, and then there's word embeddings, and there's text matching. So I'll be taking one-on-one, and let's see what we have for this. So what you see right now in front of the screens is text processing. So usually text processing is something that is done on data which is not really clean, or I would say in a sort, there's a lot of noise present. So what you have to do is you have to clean the data first. You have to make it noise free, and you also have to make sure that it's pretty feasible for your analysis. So what you do is it consists of the three steps that is, that's right there on the screen. Noise removal, lexicon normalization, and object standardization. So noise removal. So what happens is any piece of information which is not relevant to the context and is present, that's usually called noise. So let's assume usually a lot of data has etc., or it has a lot of dots, and you might not specifically wish to consider that. So that is when your noise removal comes in. To be more specific, you're just cleaning out or weeding out your data so that you get the good feasible amount of data for your work. Next, we have the lexicon normalization. Let's assume we have, I give you 4 words: play, player, played, and probably player. So what you see is all these 4 words have their root of play. So that's where the lexicon normalization comes in. What you're basically doing is there are they are different variations of the word play, so they are contextually or similar. So you can, in a sense, group them together to make them sort of lexicalized, normalized, if that makes sense. After that, probably we have object standardization. I would say, we probably have a habit of slang. We use DM for direct message, and we use BRB for be right back. So all of the short-term messages, or all of the short-term contexts, which you might not necessarily want to show in your data or in your parsing, but and you have to get rid of them. That's when the object standardization comes. So once your noise is removed, once you have lexicalized, normalized data where you have all of this removed out, filtered out, weighed out, even the object standardization is done, that's when a pre-processing part is done. That's good. I'll probably do one thing. I'll be sharing my notebook with you, so that it can make things easier for us to work on. Yeah, I hope my OneNote is visible now. Is it visible? Cool. So let's talk about this in some of the most fundamental terms. What I wanted to. So let's assume we are beginning with the raw data first. Now, once I have my raw data, I would probably like to do some sort of cleaning in it. So I would say probably the URLs or ETCs or any sort of short words that might necessarily confuse our machine translation system is what we're going to put in this. Once that is done, we can probably put in the terms of just a sec. Yeah, so once that is done, we can probably lemmatize our data, or we can perform path of speech tagging, or any sort of tagging that can be done with our data, which we think can be done. And once it has been cleaned up, once we have some basic operations performed, you might want to do a sort of I would say a dictionary checkup, or a lookup in the table. So I would better say lookup in the table, or dictionary check, so that system gets through a couple of words which are not there in the dictionary already. It can add them in, so that might make sense. And once that is done, you get your clean filtered out data. So I would rather say this is a clean data. So this is a rough sketch of how exactly this should be done. You have your raw data. You have your stop words or URL or punctuation or mentions, anything which you usually refer to this as the noise entity removal. We would want to remove all of this, and then we have the word normalization, which you can see, we have lemmatization, or you have POS tagging or stemming or tokenization. Once that is done, our last step would be to do the standardization of word, where you would want to do the lookup tables, or maybe regular expressions, or maybe the dictionary checkup. Once all of this has been passed on, you would get a clean data. So this is how the rough sketch should be. I'll be getting back to my PPT now. Right. So I wanted to give you I just wanted to give you an insight on how exactly the clean data is processed. So once you have that, our next step is the syntactical parsing. So this is one of the most interesting parts, and one of the parts which every beginner should do. So you have something like dependency grammar. So what you need to do for this is, once you have a particular sentence, let's assume that you have some sort of sentence. So you're supposed to build a tree. For that, you can probably refer to my previous videos. I've created a couple of videos in a that you could join the name. So what we're basically doing is, usually sentences are composed of words which are together. So what that means is, you need to know basic dependency grammar so that you can form out a sort of dependency tree. So let's assume you have some sort of particular sentence. You start with the root word. Once you get the root, you create again some sort of two subtrees, and a sort of subtree pattern comes in, because it's tree, subtree, subtree, and you get the overall look of it. That's the dependency grammar for you. And then we have the part of speech tagging. It's called POS tagging in a short term. So we know POS tags are noun, verbs, adjective, adverbs, etc. So what we're doing is, we are basically tagging each of the word of our sentence with a POS tag. So let's assume I given a system. I given a statement to my machine translation system. I am speaking here PyCon Africa. So my system would take in the I as PRP, which is the pronoun phase, and M as the VBP, which is the verb phase, and speaking as the VBG, which is verb happening in the continuous form. So this is the basic output of the part of speech tagging, where everything that you're sort of doing is getting tagged up. So that makes up your syntactical parsing. Then we have the entity parsing. So this gets sort of interesting. So we have the phrase detection, the NER, the named entity recognition, topic modeling, and grams. So I would like to start with probably named entity recognition. So let's assume I have a sentence called probably something like X is the CEO of Google. So here my X is the name of the person, and Google is the name of the organization, obviously. And Google, I say he is the CEO of Google at New York. So New York is location. So my named entity recognition will, in short, put in the name, location, organization, all of it into the view of the machine translation system, so that our system becomes smart enough to detect that once there's a name, once there's a location, it'll automatically sort of recognize or detect that, all right, so there's a location, so probably he's talking about somebody, or he's talking about an organization, so maybe I need to link a tree. So that's how the basic machine translation model works out. And then you have the topic modeling. Topic modeling is simple. Probably if I talk about, let's say, prevailing in the COVID situation, I talk about health, doctors, treatment, anything on those terms. It closely matches with the term of health, or at least with the probably talk of doctors. So it all of this is being referred to a topic, and these topics get within themselves, and that is how the topic modeling comes in. So when you have the name entity recognition, the NER, along with the topic modeling, when you club these two, you have an amazing system of a recognition or an entity parsing, where a system will be very smart enough to detect, all right, so there's the situation of COVID being discussed. I have the location, let's say, I can say that the cases are pretty bad in India. I mean, the the situation is really bad in India. So our system would be smart enough to detect that, all right, cases are really bad in India. So this is, the user is probably talking something negative. So I might have to probably, put it in the same terms. So that's how you make your system smarter. And n-grams, it's basically you put in, sort of, I would say, let's assume n-grams is probably compared to words. So there's a criteria. Let's assume your n-grams is more than one. It's called unigrams. And when you have n equal to two, which is a bigrams, what you do is you basically club the two words together which have the same word. I mean, let's assume I say this is a sample text. So this and is match up along with is and a, along with a and sample, and along with sample and text. So what happens is we are creating an n-gram so that it can help our it can help our machine translation system to efficiently detect if there are a lot of chains happening up, or there's a chain reaction happening in a sort of manner. So that's your n-gram. So this completes an entity parsing. Then we have the statistical features. This is really interesting. I've written about TF-IDF and frequency density features and readability features. So TF-IDF, it stands for term frequency inverse document frequency. So in its most simplest term, it is used for information retrieval problems. And the TF that you see in the beginning, it's called term frequency. So what that means is, let's assume you have a document T. You look out for a term T. There's a term T. So the term T is defined as the count of that same T within the document. And IDF is basically logarithmic of the ratios of the total documents coming in. So your corpus is basically a list of documents. So your corpus will define probably how many number of documents are coming in, and how many number of the counts of the same text or the counts of the terms coming in. There's another formula for that. I would not be going into the mathematical aspect of things right now. And then you have the frequency, or probably the other features of readability. So here you focus on the word count, sentence count, punctuation counts, probably the industry specific word counts, so that whenever let's assume I talk about PyCon Africa. So PyCon Africa is a specific word count. So as soon as I see PyCon Africa, it's going to increment the counter. And at the end of my translation, my machine translation will tell me that there were a number of PyCon Africas occurring in a particular sentence or in a particular document. And probably your machine translation system should work more on probably efficiency of the machine of PyCons occurring. I mean, once there's a PyCon, the next word could be Africa. So that's how you train a model to be more efficient. That was about the statistical features. Involves a lot of maths, heavy maths. So you better be good at maths for that. Then we have the concept of word embeddings. Word embeddings, this is a topic of vectors. So vectors are very similar to what we know in mathematics. Probably we know that the high dimensional word features are mapped with the low dimensional feature vectors. And what you do is you basically create a sort of array. You create a neural network. You create a shallow neural network called skipgram. And what you do is whenever a sort of sentence has been entered into a model, you try to train it, saying that if there are a specific number of word embeddings, or if there's specific number of vocabularies, you try to I would say train or the terms. This might seem out of the blues right now, but then word embeddings are helpful when you're building a really sophisticated machine translation system, specifically when you're dealing with a large data set. And last, we have the text matching. So we have the Leontief distance, Fionatic matching, and the flexible string matching. So I will not be going into details of this because this is involves heavy maths. But on a lighter side, a lot of these have a correlation with the specific distance between two terms or the two words that you see. And what basically it does is it just finds the distance, and if it sees if it makes sense to sort of put in the next word. I mean, just like our keyboard autocorrect works. So it works on the same work of text matching it. I think this was too much for what NLP might be. talking about some standard components of a machine translation system, these 5 are roughly the components that you might need. So, you have first word analyzer. Word analyzer is very similar to what we had discussed in a previous slide on the word grouping or word matching. So we word analyzer probably works on the lines of morphological analysis. So we have 2 terms here. You should be well aware of them. So one of them is called GNP, another is called TAM. So GNP is called gender, number, person, and TAM is called tense, aspect, modality. So what it does is basically whenever a word of a sentence has been entered in, it tries to put in, it tries to give specific wordings to a specific word. It sees if let's assume I given a noun, or let's assume I give somebody's name. It says that the GNP, or the gender noun pronoun, gender noun person, it defines if if it is talking about a specific gender, if there's any number of people involved there, or is there somebody being discussed in that aspect. And tense, aspect, mobility, it talks about what sort of case is being discussed. Is it being about past or present? And this is very specific to the Indian languages, so it might not actually make sense to the languages which are derived from other continents. So just brief up. And then we have the local word grouper. So this works similar on the terms of word analyzer, but as the name is suggesting you, this literally groups words. Whenever we have sequences of words that have a meaning which cannot be composed out of the meanings of individual words, they must be grouped together, and the group as a whole will have a meaning. So this meaning will then be stored in a table that was discussed in the previous slide. So what I'm trying to say here is the local words which might not specifically make sense in a given frame of time or in a given specific document, you try to group them together and you try to add them into your dictionary, and you keep it for a future reference as well as for a present reference, so that it helps you in a good mapping of your probably machine translation system. After that, we have mapping using the bilingual diaries. So usually when you're translating from one language to another, obviously there'll be a lot of dictionaries involved. So what you basically do is doing this is once you have a specific word of one language and you want to convert it to the second one, you try to look up the meaning for the first one in the dictionary, and you try to look at for its pronoun or its noun in the target language. But you also take care about the GNPs and TAM that was discussed above. You need to make sure that the same number and the same person is being discussed. I actually cannot show a code tutorial right now because I think we're running low on time. So I would just discuss it on air that mapper using bilingual dictionaries is one of the most simplest manner of mapping things directly from the root word. And then we have the word synthesizer. So it is basically the reverse of word analyzer. It takes a root and it takes its lexical category and grammatical features, and then it generates a word. So again, this is very specific to the Indian languages, but it is a much simpler task compared to the word analyzer. This can be done directly. You do not really have to go by other alternatives of proposing or testing and so on. And the last one says putting the components together. So once everything is done, you're all set. You put in all of this and you get a machine translation system. It's that easy. I mean, it sounds easy, but definitely is not. So first, the input text in a source language is passed to the word analyzer, which analyzes each word and it produces its root and grammatical features. And then these are fed into the local word grouper, which combines the words and produces local word groups. And then the mapper takes the output and replaces the elements of the source language with the elements of the root language. And so and so you work on with your features of the word synthesizer in case it does not match up, and then you put together, and this is your machine translation system. So these were the components of machine translation system. And Anusaaraka, the research work that I'm talking about, these are its roughly the features that it has to give out. So number one, we have the faithful representation. of text in source language. So what this means is, as I told you earlier, when you give out a text in English, and suppose assume that you have to convert it to French, and there's not good, you know that when you feed it into Google Translator, it directly gives you the word, but it does not really show you how it happens, or it does not show you how many. So the Anusaaraka research work that's being done, it helps us in the faithful representation and also the reversibility. Let me explain. So faithful representation is, we or the software tries to make sure that the user is understanding the information which is contained in the English sentence, because these days a lot of information is available in English and not in the language that might be a mother tongue, or might be a language that is necessarily not English, and something that you might find something easy preference to. So it would actually be pointless to have a translation that reads well but does not truly capture the information of the source text. So what we do is, we do not really focus on the translation. We do focus on the translation, but we do not focus on reading. We focus on capturing the information of the source code, and this is very unique to our software. And we also see that, probably at every step when your information is given in, it is given back with damage of information that can be avoided is done gradually. You obviously cannot reduce the damage at once, and obviously it would not be as perfect as human translation, but with some efforts and some consistent effort from the users, some sort of training can probably help you in some sort of easy translation. And reversibility is one of the biggest features I like in our system. So what happens is, usually when you're given a word, there's not much transparency. The transparency is reduced because you do not really know how many layers have been taken in. What is the confidence to the end user? Because you give a sentence to me, and if I'm a machine translator system, if I'm an MT, I can translate and give it back to you. But you must also have confidence in me that there's some sort of transparency. So, regardless of the text that is coming in, we try to give analysis of all the output layers, and we also try to give reference to the context. These are about the features. And anybody who's beginning new, although the session was marked in probably intermediate, I would say NLP is an easygoing thing, and these are some important libraries for NLP. Scikit-learn, you use it mostly to do machine learning in Python, but then it really helps you in the overall analysis of learning both machine learning and NLP at once. So in a way, it'd be a great thing if you go through Scikit-learn. And then we have the NLTK, or the Natural Language Toolkit. This is one of the most amazing tool one of the most amazing libraries for NLP, because this literally has the capability to generate a machine translation system for you, and it has almost everything that you would need for an NLP MMT, that is the machine translator. And then there's also the pattern library, which I have not used much, but I've heard that it's a really good web mining module. So it has tools for both NLP and machine learning, but I would prefer Scikit-learn because that's also being used in some sort of data analysis or data science, and some sort of the analysis that you might want to do on a documents, which might not be available on a machine translation system. So I feel that these three are the most important libraries for NLP, specifically also for a machine translation system. And this is one of the quotes which I like the most. If you can talk to a man in a language he understands, you talk with him in whatever language you want. But then if you talk, that goes to his head. But if you want to talk, if you want to go to his heart, then probably talking to him in his own language is the best, and that's said by the former South African president. And one of the most amazing things is, we are forgetting what our own language is. We are all complexicated by the English language, or we are all into English language, that we're actually forgetting our roots. So what that means is, in case you have a mother tongue, in case you have a language, and if there's not much machine translate work being done on it, if there's not much NLP work on it, you could probably be the first one to define a dictionary and probably work on it. You do not really need to care about probably Google Translate or Bing Translator. They do not really have good efficiency. I mean, when comparing to what you can build, because I feel there's a lot of scope. There's a lot of work that can be done. So if you have your own language, I assume everybody has their own mother tongue, and you can probably work really well with your own language. I would suggest you to begin with the NLP machine translation system building, and yes, that should help you. And lastly, that is all about it. I'm open for doubts, and you can contact me at this email ID for any sort of projects coming in or any sort of collaborations. And any links to my LinkedIn or GitHub are in the PyCon Africa webpage. You can go ahead.